Hi. In this video, we are going to review the IFM sensor and then proceed to test its calibration. First, we examine the packaging. It says designed by IFM, made in Romania, and the model is VKV021. The packaging seems to be original. In the first step, we take an overview. The sensor has 4 pins. It features an analog output from 4 to 20 milliamps. It is labeled as follows. Top left pin and top right pin are for power supply. Top left is positive supply, bottom left is negative supply, and bottom right is the relay output, which is PNP type with 500 milliamps output current. Here we see 2 adjustable parts. One is for the set point and the other is for delay. Let me explain these. There are 2 movable elements. The first one adjusts the set point, the vibration threshold at which the relay activates. The second one is for delay. To adjust them, first unlock the mechanism. When the sensor is installed on site, you should keep it locked to avoid accidental changes. To unlock, grab the top part and turn it until it aligns with the arrow, then it becomes movable. This sensor, VKV021, has a reading range from 0 to 25 mm per second, which is equal to 1 inch per second. The scale starts from 0 at the top and increases down to 25 mm. You can set the set point anywhere within this range. For example, I set it to 5 mm per second. That means if the vibration level reaches 5 mm per second, the relay will activate. Now, there is another setting labeled Sec Delay Set Sec. What does this mean? Sec is related to the top and bottom charts, and this sets how long the vibration must stay above the set point. The values range from 0, 10, 15 to 60 seconds. Short spikes are usually not real failures. For instance, a person may touch the sensor, or the machine may briefly generate a vibration spike. Real failures, such as bearing defects or shaft looseness, typically cause gradual vibration increase. Therefore, I configure the delay so that if vibration exceeds 5 mm per second for 20 seconds, the relay will trigger. There are 2 indicator lights, one is for power and the other shows relay status. One turns green and the other turns red when the relay is active. Another point, this sensor does not use piezoelectric MEMS technology. Keep in mind that MEMS is generally cheaper than piezoelectric and is more susceptible to noise. It also says, B millimeters per second, 10 to 1000 Hz. Most velocity sensors work up to 1000 Hz. This is VKV021 and nothing else is written on it. Now we move to the device. We mounted the IFM sensor onto a metrics shaker. This shaker has one input for millivolt sensors. It displays sensitivity error on the screen. But it does not support 4 to 20 milliamp sensors, so we connected the sensor output directly to a multimeter to read the current. I am now powering the sensor and securing the shaker. As seen on screen, the multimeter shows for milliamps, which means no vibration is present. This matches the expected base value of a 4 to 20 milliamp sensor. Now I apply light foot taps to the floor and you see the reading goes up. That means the sensor is detecting vibration. I now turn on the shaker. First, I lower the amplitude to minimum, about 2 mm per second. As I increase amplitude, the sensor's output current also increases. Eventually, the amplitude reaches 33 mm per second, which exceeds the valid 4 to 20 milliamp range. At this point, the output becomes saturated. You can see the current goes up to 30 milliamps. This is not ideal. Piezoelectric sensors usually stop at 20 milliamps to avoid overflow. But here, the current keeps rising as vibration increases. I now set the frequency to 10 Hz. Note that the sensor is labeled to work from 10 to 1000 Hz. Let's test it. I set the amplitude to 20 millimeters per second. At 10 Hz, the output is only 7.6 milliamps. I now increase the frequency to 30 Hz. Since I do not change the amplitude, the current remains stable. This indicates incorrect performance at low frequency. Let's find the lowest frequency at which it works correctly. 13, 14, and 15 Hz are still inaccurate. Only around 25 Hz the output becomes correct. Now I raise it up to 455 Hz and the amplitude is still 20 millimeters per second. The output now shows 16 milliamps. According to standard ISO 16063 Part 21, this calibration was performed in a back-to-back setup. There are two types of tests: frequency test, sensitivity stays fixed, frequency is changed from 10 to 1000 Hz and error is recorded. Sensitivity test, frequency is fixed at 100 Hz and amplitude is changed from 1 to 25 millimeters per second, then error is measured and compared with a reference sensor.